Good morning, everyone. Mechanics of Materials, Chapter 10, Strain Transformation. Let's solve an interesting problem in the calculation of change of area in a planar stress situation. In this example, let's consider a square plate which is handling a planar stress sigma y like a compressive negative 200 megapascal and a sigma x a tensile 400 megapascal in x and y directions. If the original area, if we call it A naught, is equal to 150 centimeters squared, and the thickness of the plate is 1 centimeter, nu is provided, E is 200 gigapascal, and giga is 10 to 9 pascal. And we want to know what is the change in the area. So if we just consider our original area like A naught, which is dx times dy, and after deformation, it just gives us a new area, like the bigger square, which is, we call that A naught. So if the x dimension was dx, it just changed to dx times epsilon x. Likewise, in y direction, that's dy, just changed to dy times epsilon y. And it just gives us a new area. A naught is dx times dy. A1 is dx plus this one. This is our new, for example, x prime times dx prime, for example, dy prime. And if you do the math, it just gives you this one times this one, this one times this one, then and if you do the math, it just gives you, if you do the math and factor out A naught, which is dx times dy, it just simply gives you 1 plus epsilon x plus epsilon y plus a multiplication of epsilon x and epsilon y. And that's very close to zero. We are almost neglect that because epsilon itself is pretty small. And if you just have multiplication of two of them, that's very, very small number. And definitely change in area is simply A naught minus A naught, A1 times A naught. So the new area minus the original one gives us the change in the area. So let's go back to our equation and just consider our case is a square. Note 1. Our shape is a square, so it's almost our dx and dy is the same, but you can apply, the reason I just put it like different, if you apply it to a rectangular plate, that's the same issue. In our case, dx is equal to dy, but it's easily can apply to a rectangular a plate as well. And the more important note number 2 is by the stresses applied to the sample, we don't know how it forms. For example, it might shrinkage from y sides and just it might have this kind of shape. We don't know what's the reaction. It just depends on the direction. So if it just pulls the plate from the side and push it from the up and down and pulls it from the side, so it can uh, like deform like something like this one. But the point is that's not the point. As you can consider any kind of shape, you just need to consider dx and dy and dy epsilon y. and due to Poisson's ratio and the direction, be careful about the direction of your stresses. So it should, then it just automatically applies that one. So we do not know for sure what is the new shape, but we know, but you can draw it anyhow you want and just add this part. If it's just in a push, it just subtract it, and if it's in a pull domain, it just a add it to the original size. That's the important note. I hope I made it clear for you. So as soon as you calculate a1 and simplify it, so that's and factor out a naught. A1 is 1 plus epsilon x plus epsilon y in bracket times a naught, and then definitely delta a is simply new one minus the original one. So this is our a delta a, which is epsilon x plus epsilon y times a naught. You can also flashback to the Arial strain, and when if you remember, epsilon a is epsilon x plus epsilon y, and this is the formula for epsilon x, and then this is the comprehensive formula for epsilon y if we have also sigma z, which is in our case that's 0, and it just gives us epsilon a or epsilon x plus epsilon y is equal to this equation. And because our epsilon sigma z is 0, we don't have this term, so that goes 0, and we just left with this part of our equation. So Arial strain is 1 over e times 1 minus nu times sigma x plus sigma y. If you replace the numeric value, like e is equal to 200 gigapascal, and giga is 10 to 9. This is our new 1 minus nu. Sigma x is, just be careful about the direction, plus minus 200. So this is a tensile strain, and this is compressive, times 2 megapascal, which is 10 to 6 pascal. And if you calculate the numeric value, it just gives you zero point 0.7. Epsilon a is 0.7 times 10 negative 3, and that's dimensionless. Then if you, and we already have a naught, we calculate epsilon a, and delta a, we calculate that the delta in area is epsilon a times a naught, and that makes sense because epsilon is delta L over L. That's epsilon normal. Epsilon, we know epsilon area is delta area over the area, and epsilon v, which we call it like T E, or delta V over original V. So if we are looking for our delta A, we can simply multiply original area, times epsilon A, which is this part, epsilon A. And then if you do the math, it just gives you this numeric value, delta A times original area, and then if you convert it to millimeter square, it just gives you delta A is equal to 10.5 millimeter square. Thank you. It's an interesting problem. You can calculate the change in area just by having the stresses and Poisson's ratio. Thank you. We'll solve more problems.